Okay, I'll take in a pretty related topic, and this is competitive evolution. So we looked at cooperative evolution, there has to be a competitive equivalent of it. Imagine that there's a game, so that's a game board, and there are two players, player one, player two. I'm not sure what would they do, but that's a game. So you move something, for something you'll get scores, for something you'll not get scores. Finally, there'll be a winner, there will be somebody who lose, and that's how the game looks like. We've seen things like a tic-tac-toe game, so the cross and nuts. So you play it like this, and of course the algorithm is the mini max, but the strategy is for every state. So be it empty, be it I have a move. So let's say I need to place it cross at 2 2, and this is called as the policy. So that's a state and that's a policy. And here maybe again I place it at 2 2. Here maybe I place it at 1 3. So this means at this state, this is my move. At this state, this is my move. At this state, this is my move. So we calculated it using expecti max, of course, using minimax algorithm, of course, in AI. If I want to do it using evolution, it's simple that I can. So this all is all states. It's like a rule table. In this state, do this. In this state, do this. So this part is constant, all the states, and this part is variable. So I'll optimize this up. In general, of course, we know that modern day games, the number of states are ridiculously large. In fact, they are continuous, so there's no discretization as well. So, if it's continuous, so I say that this agent, what does it do? It has a neural network, so it has a ANN, and the sensors are the input and the move is the output. In some games it's up down right left. Now of course I can use the reinforcement learning again, and it's a very similar algorithm that I'll be using, except for I'll use evolution instead of reinforcement learning in order to say what is good for the game and what is bad for the game. And again, I need not really repeat. I really need not repeat. So let's find out which step is a problem. So this could be a RNN, of course, and this is for player one. Many games, player one and player two have different rules. So, and similarly, the sensor and the RNN for player two. So I need to learn a player one recurrent neural network, and I need to learn a recurrent neural network for the opponent as well. I need to learn two recurrent neural networks. So we'll do both using neuro evolution, and again it's good to think which one is a problem. So I start over with the initial random population pool, not a problem. Fitness evaluation, then a problem. Scaling given the fitness, just sort it up. Calculate expectation value, not a problem. Selection, not a problem. Standard things will work. Crossover mutation, not a problem. Making new population set, not a problem. The only thing that's a problem is what is a fitness evaluation. So I need to do something so that I'm able to calculate my fitness function values. I should be able to say how good or how bad it is. And this looks like a cooperative co-evolution thing itself, because there's no fitness function, and what's more is your fitness function value depends on your opponent. So if you're playing a cricket match against a weaker opponent, Bangladesh, your performance will be good. Playing it against a stronger country, Australia, England, your performance will be bad. So it also depends upon the opponent, and similarly for the opponent, if the opponent is playing it against a weaker team, it'll be good. If it's playing against a stronger team, it will absolutely be bad. And that's the one that causes in a trouble. So we need to solve this trouble, and we'll go exactly the same way as we went in cooperative co-evolution. So what do we do is that in both of them we take in the best represent. We take in a population pool. So that's my population pool. Very informally, that's my population pool. Very informally, these are my best few individuals, same as cooperative coevolution. So I need to do a fitness evaluation of all of them. Let's do it for one individual, and if I can do it for this one individual, I can calculate what the fitness function value is. Then I will say it similarly for all others. So let's say it's for this one. So let's say I'm doing a fitness function evaluation of this one, and therefore what I'll really do is I'll make it play. So let's call this thing as X, and let's say this is best player number 2 1, player number 2 2, player number 2 3. So I'll organize matches X versus best first player, best second player, best third player, and I'll take the average score. And that becomes a fitness function value. So that's the score, and that is what becomes the fitness function value. Am I able to defeat all of them? I'm not able to defeat all of them, and that's one proposal that you can consider. So every game has a score. You say you compete with the best 3, best 4, best 5, best 6 of the other representatives, and then you play matches. Then it's up to the game to give you a score and to give the other opponent a score, and your score is the average out of all the best people that you compete with, and based on that the best individuals will also update themselves. The best representatives will also update themselves. And unlike a cooperative coevolution, if the game is binary at 0 1, then most of the individuals will either have a fitness value of 0 or 1. So you need, instead of just best 1, you need lots of best individuals. As well as now you might even archive in individuals, the ones who died, just to see that how do the individuals play against these people, and can they still, if they cannot defeat the bad players, and they are very bad. So now your collection might even have some bad players to see just that are the good individuals in a position to defeat the bad ones. So you can make a good collection, a good archive of population pool. It may not really have only the best, it can also have some average or poor players which have died, but still they are just used as a reference point to evaluate the other players. Now, briefly coming on to what really happens in a different setting is many times the games are such that yes, there are two players, which is player 1 and a player 2, but then the player 1 and player 2 are virtually doing the same thing. In the context of the game, the actions may be opposite. Like for a tic-tac-toe, one is using cross, the other one is using O, but they're doing exactly the same thing, getting 3 of the same type. So the game from a player 1 context can be exactly replicated as a game in the player 2 context by changing X's to O's and O's to X's. Similarly, lawn tennis, so the only difference is the field swap, and everything remains exactly the same. So a good player 1 in this side will also be a good player in that side. It's just that the context will change. The left becomes right, the right becomes left, and so on and so forth. So carom, the black becomes white, the white becomes black. So a good player in the first part will become a good one in the second part. They will just change these conventions. So that's what are most of the games. So the previous definition as a straightaway carry forward from cooperative coevolution was just a carry forward. There are more practical games where you cannot get, where one thing requires a separate skill, another thing requires a separate skill. Cricket is one where, yes, batting and bowling are two very separate skills. So great batsmen are not great bowlers. But then in games, when you look at it, you can make contextual level changes. X's becomes O's, and then a good player of X's is also a good player of O's with just a change of the context. So now what I do is, because of this thing, I take in, instead of two population pool, just one population pool, and let's say this one is my population pool. So these are great tennis players, these are great football players. Okay, that's a team event. We are considering only individual games. Good table tennis players, good whatever. These are good players of the sport. And now I want to do exactly the same thing. So again, fitness evaluation is a problem. Crossover is not a problem. Mutation is not a problem. Selection is not a problem. The only problem is fitness evaluation. And if I can evaluate the fitness of a random individual, I can do it for all of them. So let's say this one is X, and let me evaluate the fitness of this individual X. Now the problem is, what do I do? There are no representatives. Again, if there are representatives, many will be able to defeat, many will not be able to defeat. Ideally, I'll have a representative that nobody can defeat. So the traditional approaches don't really hold. How do I give a fitness function value? That's a problem. How do I give a fitness function value? And therefore, what do I do is, now instead of giving a fitness function value, I change this thing. So I say, instead of giving a fitness function value, which I cannot give, let's give a rank. So the problem now becomes that I've got some individuals and I need to rank them up. 1, 2, 3, 4, 5. So I should be able to give them rank, because in any case we use a rank based scaling. So the expectation value is proportional to rank. Rank 1 is the highest expectation. So in any case, from fitness function value, I only get the rank. So why not compute ranks directly? And turns out that I really don't need to tell you about how to calculate ranks, because whichever sport you follow, there is a championship, and the championship gives rank to all the teams, and I'll use exactly the same thing. So the best technique is, of course, if you want to give in, so the best technique is, of course, you make matches, you play matches between every two people. So this plays with this, 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 blah blah. So I say play match between every two individuals. So goodness of a individual is equal to number of opponents defeated. So any championship uses this. 2 marks if you win, 1 mark if you tie, 0 marks if you lose. Total it up, and then you get your rank. So exactly the same thing. And if you know sports, then of course you'll know that there's a problem in this one. So the problem in this one is that there are n square matches. That is too many matches. There are too many matches, and this is of course a round robin. So every player plays with everyone else. So that's a problem. That is absolutely a problem. So there's another technique which does not have any matches. Remember, n log n is the complexity of the genetic algorithm and most evolutionary algorithm. So where log n is because of sorting to get the ranks, as well as log n is because of the selection of the individuals. So I need to improve that. N square is increasing the complexity from n log n to n square of the genetic algorithm, and that's pretty bad. So The other one is also something which is fundamentally known. If there are five teams that want to play a championship, so I randomly paired two. Then I randomly pair two. Then I randomly pair two. And then whoever wins here is the one who wins. So this becomes rank 1, this becomes rank 2, this becomes rank 3. So for a tree with n individuals, so there will only be n matches. It's a binary tree, so there'll only be n matches. The problem over here is that you may be very good, but you are having the first match with a world champion. You may be good, but you have the first match with a world champion. It's a knockout. Of course, that's a round robin, and this one is knockout. So you lose one, you're gone. So you may be good. Your first match was with a world champion, so you knocked out. So your rank is very bad. You are last. N by 2 individuals are last because N by 2 individuals lose the first match. All of them are last, so you're one of the last. But then ideally you were very good. It's just that your first match was with the world champion. So this one is bad from that context. So round robin is bad because of n square matches, and this one is bad because they are, I mean, the ranks are not very reflective. So what many people do, of course, we use pool. So that's pool A, that's pool B, that's pool C. So you say that there are n by k pools of k individuals each. So within pools is round robin, and outside pools is what you go as a knockout. So in short, this becomes k square plus n by k. If k is very large, then you're almost going n square, and if k is extremely small, then you are almost going knockout. And that's exactly what they do in every sport. So I need not even tell you pool A, pool B, pool C, pool D. And then teams will have a problem. My pool has all the best players, same as the problem with the knockout, and that pool has very weak teams, and there'll be politics over it. So that's a problem. But then the good thing is they are just k square matches, k square plus n by k. So they are just k square matches. After that, you play a knockout. So between the good individuals, then you play a knockout. So unlike the round robin, it reduces the number of matches significantly, but it still has problems of the knockout matches. Now, once you play in these matches, once you get into all this, once you have a population pool, all that you do is you had to get given the rank. So using this, you rank in all the individuals of the knockout, and then you rank in all the individuals of the pool based on the points table, based on the score. Once you get the rank, exactly the same as those that done in all the sports championship, then you get the rank of the individual. Now when you get the rank of the individuals, then you have this thing over here. Let me draw it up again. So I had a championship. So there were two players that play it up. So what did I do? I started off with a random population pool like this. I ranked them up. So I got in the ranks. So how did I do it? I organized a championship. I randomly gave them pools. They competed them with the pools. Then the best players of the pools went into the knockout series, and then the knockout series was organized. So I gave in the rank first to the knockout series winners, and then to the ranks. And I get in these ranks like this. Once I get in these ranks like this, then I applied normal selection, crossover, and mutation. So all operators. Now, like the cooperative coevolution, the evaluation was against a changing fitness function as a representative of the other population pool. Exactly the same thing happens over here. So the individuals are changing, the ones whom you are competing against are changing, and that's why the evolution is a lot more harder, and that's also what you practically see what happens. So many times what will happen is you get in for, let's say, a lawn tennis match. So a player who has a beautiful service, so mostly aces, so beautiful, unplayable, so that player beats everyone, becomes the world champion for a very long time, so just because of one trick shot. So before that they were grandmasters, before that they were people who played beautiful tennis, but then didn't have this one skill to play this beautiful service deliveries, and therefore they are now nothing, and this man is winning. And therefore more people start copying this man, his mutated versions. So his children, mutated versions, they also start come, and those populations dominate, which can do those beautiful services. And then suddenly you've got people who can play these beautiful services and actually play them such nicely that the delivery of those service is unplayable. So then this champion is into nothing, because the anti of the his beautiful service has been found, and now those skills are selling hot, and people who can do that are getting nice ranking values. So players keep on developing the skills, and the opponents keep on developing the counter skills, and then you all develop more skills and more counter skills. All those genes get developed, all those weights and biases, all those features get developed into a neural network. It's extremely unstable because the opponents whom you play against are continuously changing, they're continuously improving, so you have to improve with time in order to survive. One thing which is done is that in such kind of systems where you inspire others, others inspire you, you inspire others, others inspire you, and you keep on competing and growing because of this competitiveness. Something that happens is sometimes you can unlearn a skill. It's just because of the fact that that skill did not appear to be very useful for now, so you just unlearn it up. In neural networks, you don't see your data for a long time, you unlearn it up, and therefore sometimes what happens is that the rank is based on two factors. The first is rank in the championship, which I discussed, organized between individuals of population pool, and the second one is the number of opponents defeated in an archived population. The archived population is nothing but past, maybe deleted individuals that are diverse. So that's like just a bank of individuals, just a bank of players, just a bank of neural networks, just a bank of people who previously were good, eventually died because of not having a skill or something like that, but they have some diverse content. So you maintain a bank of such individuals, you maintain a bank of such players, you maintain in a bank of such recurrent neural networks, and ensure that if an individual is very highly ranked out of the current players but it cannot defeat a past player, because of some reason, some limitation, the past player may have died. If you cannot defeat the past player, then also your fitness is wrong. So there are two indicators of fitness. One, out of the current population pool, how good you are, the best of the best, they have survived so long. Secondly, can you at least defeat the past players as well? Can you defeat the players who have now died because of a lack of performance? And that makes sure that some skills which are necessary are not just lost with time, they are retained in this archival population. And similarly, when you delete individuals, you might just add a few diverse of them into the archive population. If you make the archive population too much, then of course it affects the computation time. So now you need to play the championship, and you also need to play archive population. So if there are M individuals in the archive population, there are M matches which are straight away increased. So archive population cannot be too large. It cannot go with time, but you maintain a archive of old players, archive of previous players who were once good, now died, and see how many can the individual defeat. So there are two indicators of the fitness function value, and you take both of them in order to decide how good it is. This one also, the population is changing, so your fitness function is changing, and so therefore you need to continuously outperform the individuals, and therefore the evolution is slightly unstable, as well as the archive population is stable. So that makes the evolution a lot more hard. But then what's good is it's really interesting. So imagine that there's any general game, there are players, and you can evolve how the players evolve with time. You can make better and better recurrent neural networks along with time. What you can do is to have these populations or players mutate, cross over, and develop great players along with time. And by doing that, you'll have one of the greatest players of the game. Again, practically what happens is that the initial individuals will be just random bad players of the game. So again, you might use, for video games especially, collect a lot of data by people playing the game, using their data to train initial few neural networks, and then doing a neural evolution over it, rather than just training it from scratch. That will initiate or accelerate learning quite a lot. Otherwise, random players initial will be very random, they'll play randomly, and that'll delay learning. If you provide the human data, those are still competitive neural networks on a data which is generated from humans, and therefore those are stronger neural network with a lot of bias, which can of course be problematic. Everywhere you'll see a problem with the bias along with computation time. So if you want to reduce the computation time, there's some bias which may need to be inserted. So competitive evolution is the competitive equivalent of cooperative evolution. Here, a group of people, a group of players, they compete with each other, each one saying, I am better, I am better. And in doing that, they develop certain skills which are important for the game, while the game or the system is adversarial in nature. So there's only one winner, there's only one grand championship who has the best skill. It has emergent properties because the player develops skills more than it would have done while just playing on its own. So it plays with others. The poor ones die, the better ones replicate, and in short, that's how we get in the best players for video games, for any system which is adversarial in nature.